So let's talk about the normal curve. We've been talking about it a little bit, but the normal curve is symmetric. It has one peak. And this is what we call this bell-shaped. It also fits the same rule of a density curve. The area under it equals 1. For a normal curve, basically your median and your mean both lie in the center. Actually, your mode does too. Most common number happens in between. The way we set this up is, if you remember when we were talking about z-score, and I said pretty soon it'll all kind of make sense. When we were doing z-score, I think we found out that the mean was 80. And it had a standard deviation of 6.07. And this was a couple lessons ago. And I was saying that one standard deviation away from the mean would be, you take the mean and add 6.07 and get around 86. And one standard deviation away from the mean in the opposite direction was around 84. And we also transferred that into z-scores. So what happens is let's say this was at 80. Here would be our 86. And here would be our, of course, it's 74. Here would be our 74. There's a certain rule to this saying that 68% of the data lies between one standard deviation of the mean above and below, the combination of the two. So you can think of it as 34% on one side and 34% on the other side. It's basically almost the majority of the whole curve is located one standard deviation away from the mean. To go another standard deviation from the mean would be to get another 6 higher. So maybe 92. And maybe around 68. To the next standard deviation, we say that's approximately 95% of the entire curve. And it really looks like it, there doesn't really seem to be much extra room for me to do anything more with this. It's almost the whole entire curve. Another standard deviation out, and I should have made that a little longer, is out to about 90, about 98, and about 62. And we say that 3 standard deviations away from the mean is about 99.7% of your data. So how this transfers to our z-score, our z-score was very similar. If we're changing, that's a terrible picture. If we're changing our numbers to a z-score, it's going to be the same thing. We're going to use mu for our mean. One standard deviation, remember that was the lowercase sigma, away. And what we were showing on a z-score was that it was -1 and +1. And the mean was 0. So with a z-score from -1 to +1, it's going to be about 68% of the data. 2 standard deviations away from the mean is going to be that 95%. And 3 standard deviations away from the mean, which is a z-score of 3, would be that 99.7% of the data lies within there. So this rule is called the 68, 95, 99.7 rule. And what it means is approximately 68% of the observations fall between 1 standard deviation of the mean. Approximately 95% of the observations fall between 2 standard deviations of the mean. Really sloppy. And approximately 99.7% of the observations fall between 3 standard deviations of the mean. And that works the same way with z-scores. So keep in mind, the rule to finding the z-score was the same way. The z-score, or the standardized score, and what we're going to call this is the standard normal distribution. So z-score, before we were calling it the standardized score, same type of thing where you take the value, subtract the mean, and divide by the standard deviation, and that gives you a z-score. So just like we had done before, we calculated it with the mean as our x, and we got a z-score of 0. So the mean is always 0. If we were to be 1 standard deviation away, it will work out to a z-score of 1. If it works to be 1 lower, it'll work out to -1. Another thing is that you can kind of break this down in many different ways. If you have a standard normal curve, you can calculate a lot of things about this. Since you know right in the middle is your mean, and 1 standard deviation away is a z-score of 1 and -1. And these will be symmetric across the board because the standard deviation stays the same, so you want to be the same amount of spaces away. But let's say you were just going to be finding parts of it. Like, let's say you just wanted to find this end part here and beyond till the curve ends. So you can calculate this because you can say, all right, 68% land here. We already talked about 95% landing here. So you can easily kind of start calculating what each one of these parts is. And you can start breaking it down where, like, to me, this is about 34%. This is about 34%. So then I need what these other parts are. 95, take away 68. So these ones are 27, half of 27. About 13.5% for this spot, 13.5% for this spot. And keep in mind, below the mean is also where the median is. So from this middle point and below, that's 50%. So now if I want to know, I could add 34 and 13, and that'll give me right about there. 50% plus 34% plus 13.5%. 97.5%. So what's left over for me to have up here in this black part is what's left over from 100. So the percent of observations that fall in this black area is 2.5%. Now keep in mind, it doesn't just end at like 4 or a z-score of 5. It can keep on going. It's just less and less likely it's going to occur. Keep in mind also, remember Babe Ruth's score, his z-score, was like a 5. It's like almost impossible to get a 5 for a z-score. I mean, think of how far out he must be. He's that extreme outlier to be at that many deviations away from the mean. And like Barry Bonds and stuff, they were all located around the 3 mark. But Babe Ruth was located all the way out at 5 standard deviations away from the mean, a z-score of 5. So that's what made him really, honestly, so special when you start thinking about it in comparison to his peers.